underway. So in the last lecture I derived the fundamental solution for which looked like this. Okay, for the diffusion at some time t resulting from an initial concentration distribution time t equals 0 that was all concentrated at a single point. In this case, it would be about the point x is 0, like that. Yeah? And so it is a Gaussian in shape. The variance of the Gaussian increases linearly with time. The height of the Gaussian decreases in time to make sure that the total amount of material stays constant. We know that has to happen because when we were deriving the diffusion equation, we used the conservation of matter as one of the fundamental things. So if our solutions don't satisfy that, we know we must have solved the equation wrong. And just at the end, I was pointing out at the end of the last lecture that this is a symmetric, or if I'd drawn it even better than I had, this is intended to be a symmetric function about the y-axis, about x is 0. And that means that if I imagine now a slightly different situation where instead of a sample that extends to minus infinity and plus infinity in both directions, which is sort of what we implicitly assumed when we did the Fourier method for solving the diffusion equation, but if instead of that it were just to be a unilateral, a semi-infinite domain, and we were to start now, we was again to put a sort of a point source. Initially, all of the concentration is in the plane x is 0. Okay. In practice, what does that mean? In practice, that means, of course, samples aren't one-dimensional. Everything is three-dimensional in the real world. But what it means is I have a semi-infinite slab. Okay, so the material extends all the way into the x greater than 0 space, all in y and z directions, and the surface of the material is the plane x equals 0. And essentially what I'm talking about is depositing onto the surface some material at t equals 0, which is then going to be free to diffuse into the material. Then the boundary conditions there that what you'd want to do there is you'd want to solve the diffusion equation in the domain x greater than or equal to 0. You need to satisfy the boundary condition that at t equals 0 the concentration is 0 everywhere except at x is 0. And you also need to satisfy a boundary condition on this surface. And the boundary condition that you would want to satisfy on this surface normally is that the flux through that surface is 0. I don't mean the flux of material that you've deposited on the surface into the sample. What I mean is there can't be any material that sort of diffuses from the right towards the plane x is 0 and then goes through to the left, out of the sample. Okay? You know, you can imagine that typically what you might be talking about here is something where you've got a metal like gold and you've got some radioactive isotope that you've deposited on the surface. The gold is only going to diffuse into the gold. It's not going to start diffusing out into the space, the air to the left of the sample. Okay, so the boundary condition you'd have would be a Neumann boundary condition on that surface, that the gradient of the concentration is as shown here, and therefore you expect that solution to look like that. And the point is, this fundamental solution that I've got here satisfies the diffusion equation in this domain, and by its symmetry it also satisfies the fact that its first derivative is 0 at that point. And therefore actually this must be the form of the solution to this problem as well. The only difference is as I hinted last time, is that because all of the material that you deposited must diffuse into x greater than 0, there actually is twice as much there as there would be if half of it went to the right and half of it went to the left. So you have to take your fundamental solution and you have to multiply it by 2, which cancels the 4 in the square root, in order that when you integrate this up, it again integrates to the total amount of material that you deposited on the surface to begin with. Okay? But there you go. There is the diffusion equation, and one way to measure diffusivity, for example, would be to take, to heat this thing up, leave it for a long time, allow diffusion to happen, then go and start taking slices through this material, measuring the radioactivity, for example, measure the quantity of the radioisotope, so you could map the concentration, and you could do that. And what you should find is, if you did that for a load of different samples at different times, log C would be a constant, log of a constant that only depends on time, minus x squared over 4 dt. So you ought to be, if you plot log of concentration versus x squared, you should get something and be able to pull out something to do with the diffusivity as a result of that. Now what I've done there, you'll notice, is that I have implicitly assumed uniqueness for solutions to the diffusion equation. Uniqueness is something you've come across if you're solving Laplace's equation or Poisson's equation, which is, if you can find a solution which obeys the differential equation, that differential equation, and satisfies the boundary conditions, then it is the only solution. It is the right solution. And you can prove it, and I think on Blackboard I just uploaded a little thing which just sort of takes the normal proof of a uniqueness theorem for a partial differential equation and just does it for the diffusion equation. But you can see, so we can take that approach to the diffusion equation. If we just find something that works, then we've got the answer. We don't need to worry about whether there's more than one option or anything like that. So there's an example. This is an example where the sort of the initial concentration profile is on the boundary of the domain. But we could also consider a case now. So this is still a case here where I've still got a boundary between two half spaces, and I'm interested in the space x greater than 0 over here. This is where my material lives, and to the left out here is just free space. Okay. But now what I want to do is I want to consider a point source of material which is not, well, which is not, in fact, given what I'm doing, I'm talking about, I'm talking about point source in X, but of course in 3 dimensions that means a sort of layer, okay? A layer of material which is initially at point x0. Okay, so it's somehow been sort of created or deposited somehow inside the sample initially, not just at the surface of the sample. I still want to have 0 flux across this boundary because I can't have any material escaping from the sample, and so it's still the case that I want dc by dx is 0. But if I were to look at what the profile of the fundamental solution would be, it's going to look like that. Yeah? There's the Gaussian, which is now centered at x0 rather than x. So in terms of writing C of x and t, that's the blue curve so far. And the point is that solves the diffusion equation in this region of interest, but it doesn't, and it satisfies the boundary condition at infinity that the concentration goes to 0, but it doesn't satisfy this 0 flux boundary condition because this has got a bit of a slope. Okay, if I were to take this as my solution here, then this slope tells me that material is leaking out of the sample. And if I were to integrate up to under here, I wouldn't quite get the total original amount of material. And as time went on and this thing gets broader, actually more and more material would be lost. So this isn't the solution. But someone did mention last time how they thought you could do this. What was it? From electrostatics? Method of images? Brilliant. Well done. Method of images means pretend that the interface is like a mirror, and therefore that's the image. Okay, the image of the original source reflected in this mirror is over here at the position -x0. So, and let's pretend that there is also a source of material out here. And so, whoops, my drawing is really poor today. Right, let's draw that fundamental solution associated with that fictitious image. We're only pretending. Now, that would have a concentration profile that looks like this. Okay? It's centered at -x0 rather than +x0. And you can probably see what will happen if I were to take the derivative of this with respect to x. In fact, I can even do that. So dc by dx is 1 over the square root of 4 pi dt, which is a common factor, times minus 2x minus x0 over 4 dt minus 2x plus x0 . Okay, there's my expression for the first derivative of this. And if I put x equal to 0, then this simplifies, because when I put x equals to 0, I get 2x0 over 4 dt e to the minus x0 squared over 4 dt minus 2x0 over 4 dt e to the minus x0 squared over 4 dt, and you see that those cancel. Okay, and that's because, as you can see by symmetry now, the slope, the positive slope of the original solution is cancelled by the equal and opposite negative slope of the image solution. So this equation satisfies the boundary condition, the zero flux boundary condition. It still satisfies the boundary condition at x goes to infinity. And as t tends to 0, this concentration profile is going to tend to a delta function here plus a delta function here. But remember that we're only interested in using this as a solution for x greater than 0. Now, if there's a delta function out here, then for x greater than 0, when x is greater than 0, delta of x plus x0 is never going to be anything other than 0. So the image, this image solution, doesn't actually contribute anything when t equals 0 within actually the region of interest. So that's how method of images works. Again, it's different from the method of images in electrostatics, where it's used to deal with an inhomogeneous right-hand side. This is dealing with an inhomogeneous boundary condition. So it's again sort of being used slightly differently, but you can see that it's very similar. Okay. And obviously, if for any reason you actually wanted to solve the problem where you didn't have a zero flux boundary condition on this interface, but actually you wanted the concentration to vanish, Maybe because you have something that you now have something at the boundary which now hoovers up any material. Any material that arrives there gets hoovered up and taken away. So it doesn't permit any non-zero concentration. What would you do there?
Take away the...
You just change the sign, right? This would become a minus sign here rather than the plus sign, and then that would be exactly the same thing. It would solve the diffusion equation in the region of interest, and it would satisfy a boundary condition. Now you can see pretty obviously the concentration of the sum would always be 0 at the interface. Okay? All right. Is that okay? All right, that is a thing you can do. Right, we're going to go back now to the infinite domain. In one dimension. Concentration. And now I want to consider this. So I now want to consider an initial concentration profile which is 0 out here and then some constant value C0 for x greater than 0. Anyone object to that? No? Okay. Go on.
What is it now? X equals 0.
Oh, at x equals 0. Yes, okay. Probably a half.
Okay.
As it'll turn out. But that's a good question. That wasn't actually what I was too worried about. You're right, there is a discontinuity at x is 0. Yeah. Okay, there's an infinite amount of stuff there. Why might that matter as well? So if you're saying there's an infinite amount of stuff, you're saying if I integrate the concentration over all space, that's not a bounded integral. Why does that? Do you remember why that might matter? Okay, what does it mean to conserve it? That's interesting. Yes?
The Fourier transform.
Fourier transform of that concentration profile, it's a bit dodgy, isn't it? It doesn't satisfy. How would you take the Fourier transform of that out of interest, do you know? Do you know how you do that? How you deal with that issue? What you would... Go on.
Use some sort of derivative
No, I don't want to use a derivative of it because, as pointed out, if I haven't specified, it's got a discontinuity at x is 0, so it's not actually differentiable at x is 0.
Can you take a series of deltas?
Series of deltas. Well, that's actually what we'll do. But if you ever have to do this, the way you do it is that instead of a constant function to the right-hand side, you write it as an exponentially decaying function. So you write it as e to the minus lambda x. You have no problem Fourier transforming e to the minus lambda x. And then you take the limit as lambda goes to 0. Okay. There you go. Little tip for you. You have to do that. You have to do that with certain functions. For example, you want a Fourier transform a Coulomb potential. You have a similar problem. Use a similar trick. Okay. Yeah.
But still, that doesn't solve the fact that you want the concentration to integrate to 1.
Well, I don't necessarily need to integrate to 1. I wanted to integrate to a constant. Obviously, it's 1 for a Dirac delta function. And if the quantity is more, I have to multiply it by a constant to give me the constant amount of stuff. It doesn't deal with the fact that it's an infinite amount of stuff. Okay? I agree with that. It doesn't deal with the fact it's unbounded. The 1 doesn't matter so much as long as it was a fixed amount, and a finite fixed amount. The infinite amount of stuff probably won't matter as long as it's actually conserved. As long as we show that we haven't lost any, we might be okay.
But isn't the concentration defined only using 0 1?
Sorry.
Sorry. Shouldn't the concentration integrate to 1?
For the fundamental solution, yes. But look, okay, let me just write this down. Let me just write down then what our general solution was. That was the linear combination of fundamental solutions. this will help. Okay, that was what our general solution was, where we remember, yes, we did exactly what someone just suggested. We sort of build up the initial concentration profile as a sort of sum of lots of little Dirac delta function things, and then the limit, if the sum becomes the integral that you have here. Yeah. So you can imagine that as t tends to 0, the fundamental solution bit here, of course, tends to Dirac delta functions. Yeah. It tends to Dirac delta. So this so forget this for the moment. This goes with this. This tends to delta of x minus x primed. And then the integral of c of x primed, delta of x minus x primed dx primed is just c of x, which is what is on the left-hand side for t equals 0. Yeah? So it just is, do you see it's equal to itself? But at each time, the delta function for each position in space, for the amount of concentration at each particular position in space, is now evolving like a delta function, evolving into a Gaussian, and I'm summing those up to get the total concentration. So each of these fundamental solutions has to integrate to 1 all the time, but each of these for each point is weighted by the initial concentration profile. Okay? And so the integral of this with respect to x at any time, t, should also be the integral, should also be associated with this integral here, and therefore I've conserved it. Okay, I will have this solution here conserves material. The issue is, okay, go on.
Sorry, did you say t equals to infinity or infinity? The e exponential doesn't?
No, as t goes to 0.
0.
As you go to the 0, the initial condition, t goes to 0 here and here. This is delta. The delta then collapses the integral and replaces x prime by x there. And so you just end up with c of x at t equals 0 equals c of x at t equals 0. It's not very exciting, but you can see that that's how it's been constructed. Okay. In this particular case, with this naughty initial concentration profile, then there's no initial concentration outside, and of course it still goes to infinity. That's the problem, that this limit is here and the concentration is a constant C0, and this goes to e to the minus . Okay. Okay. And now you can see what the interesting thing is here about this sample. Here's how we get out of jail of this function without a Fourier transform. What we're going to do at some later point some later time is we're interested in some point x, okay, at a finite time t. That point x is somewhere inside our material here, okay, and that's going to have contributions from all other points through the material where their initial concentration, C0, has kind of diffused into this Gaussian, and the Gaussian has reached my point x and contributed something there. But the variance of these Gaussians is all the same. It's all 4dt. So at some time t, there is a characteristic length, isn't there? Which is actually square root of 4dt, which is the standard deviation of all of those Gaussians. So we know that by the time you get to 2 standard deviations, you've got 95%, haven't you, within everything. 3 standard deviations, you've got something like 99%. Okay? So if you take your point x that you're interested in, and you go square root 4dt times a small number, 4 or something like that, away from that point x, then you'll reach another point where the Gaussian that starts from that point has decayed so much that it's practically, that it's nothing. It's making no contribution. And so even though this integral is an integral over infinity, actually there's only a finite range really that's going to be allowed to contribute to the answer for a particular value of x, and that's the range that is a few 4dt's before and a few 4dt's after. So it becomes finite, and you sort of get rescued. Obviously, as t tends to infinity, this gets longer and longer and longer, but you can afford to wait. Okay, you can still do it. Okay, let's just write u is x prime minus x over square root 4 dt, like that. Then this is c0 over 4 pi dt square rooted, times, doing the substitution here, I've just done it this way, this way around, so that du is dx over square root 4 dt. So I get a square root 4 dt from the change of variable, and then I get an integral that when x primed is infinity, then u is still going to be infinity. Okay? And when x primed is naught, then u is minus x over square root 4 dt there. And then this becomes e to the minus u squared du. Alright? Now that is c0 over the square root of pi. I'm going to split the integral up into one integral from the lower bound to 0, and then one integral from 0 to infinity. Okay. This one, this is square root of pi over 2. And this one, I can actually change, if I change u is going to minus u, then the integrand doesn't change. I get a minus sign there, which I can use to flip the order of the limits around, and the limit changes from being minus to positive. So it turns out that this is just the integral from 0 to x over 4 dt. And then, so we can do one of the integrals. We can do this integral here. Can't do it. What happens when you can't do an integral? What do you do when you can't do an integral? Look it up. And when you look it up and you can't, and it's not there in terms of elementary functions, what do you do?
Do it numerically.
You might do it numerically. Shall I tell you what you do? You call it something new. Because when you call it something new, then you think, I understand it now. So let's define something called the error function as this thing. Brilliant. There we go. That's done then. That is a great way to do things. Sweep it under the carpet, exactly. The second term here, when you combine the square roots vanish, you just get c0 over 2. And this other term, once you now see why there's this factor 2 over square root pi here. The 2 over square root pi is so that when z goes to infinity, this error function tends to 1, okay, rather than root pi on 2. Okay, so it's just a bit more friendly. So c on 2, error function of x over square root 4 dt. Okay? So the error function is not actually a particularly interesting looking function. It basically does that. Okay? So it's linear in z for small z. Can you see why that is? See why it's linear in z for small z?
It's like maybe 1.
Because, yeah, for small z, if z is small, then u is always small, so e to the minus u squared is about 1, and therefore the integral is just z. Okay, so it's z, and actually you can tell the slope is 2 over root pi. Easy. And then, actually, as it goes, z goes to infinity, we know that it just goes to 1 asymptotically, so it has to look like that. So it's not a particularly interesting function, actually. But there we go. When x is naught, here, then the error function vanishes. The error function is 0 at 0, and so the answer to the question, what is the concentration at x is 0, is strictly C0 over 2. Okay, remember, that's the same thing you get with Fourier series, isn't it? If you ever expand a function in Fourier series, and it's got a discontinuity in it, like it's a square wave, then at the discontinuities, the Fourier series always evaluates to the mean, doesn't it, of the 2 points? Yeah? So it's the same here. This is, again, a Fourier method, so that's what it's going to do. Okay? So the point here is that in this particular situation, and this is not unreasonable, so we might ask ourselves, well, what's this? I don't appear to have done that yet. So what's this going to look like? I should just say that means that the solution looks like this. Again, drawn really badly. Okay, that should be at a half. Let me try again. Let me try and do this better. That's maybe better. Okay, that's at really long times. So this is an infinite sample, but we've only loaded half of the sample with stuff to begin with. It'd be a bit like saying taking 2 blocks of alloy, and one has got some extra stuff in it and the other hasn't, and then joining them together and heating it up and allowing diffusion to occur. Okay? But you can see how it sort of diffuses like that. Eventually, of course, you're going to want, as t tends to infinity, then this is going to tend to error function of 0 again, and therefore you're just going to have a concentration of half C0 everywhere. So eventually it just wants to make the concentration uniform. Now, by now you should have noticed that this quantity occurs a lot of the time. Okay? So let's call that eta. Okay? Because if I actually look back at this previous, do you see, in fact, this entire solution is a function of eta only. The fundamental solution is associated with, it's not quite eta only, but the same combination occurs there. Okay. So, let's consider the following. The diffusion equation involves a partial derivative with respect to time at constant x. With the chain rule, I can write that as a partial derivative of eta with respect to time at constant x times a derivative with respect to eta. Let's consider that. The partial derivative of eta with respect to t is a bit of a pain. It is minus x over 2t root 4 dt once the t to the minus a half has become minus 3 halves, and I've done other stuff as well. But we can see that in here there is there is still an eta sitting in here. So let's pull that out. Okay. D by dx similarly is d eta by dx at constant t times d by d eta. That is rather easier to deal with. That is that. And therefore d2 by dx squared, I would do the same thing again. What I have to note here is that when I do d by dx, I'm working at constant t. This bit here only depends on t. So this just carries straight through the derivative. Okay, so if I take a second derivative, I just end up with 1 over 4 dt, d2 by d eta squared. Okay, let's use that now in the diffusion equation. d2c by dx squared equals dc by dt becomes d 1 over 4 dt d2 by d eta squared of c equals minus eta on 2t dc by d eta. Okay, or minus 2 eta, and I'm going to anticipate now the fact that actually the partial derivative with respect to eta is actually a total derivative with respect to eta, because everything else has disappeared. All the t's and all the x's have gone, and all I'm left with is eta as a single variable. So I have an ordinary differential equation like that. Okay? Let's see if I can... There we go. Right. Now, what we've shown is that the diffusion equation can be written in terms of eta only. However, the diffusion equation itself is not the only thing that specifies the problem we want to solve here. The other thing is the boundary conditions. Yeah? So, let's think about the boundary conditions now. If I consider scaling x by some lambda and t by lambda squared on t, then eta, which would be x bar over square root for d t bar, that is independent of lambda. Okay, so in other words, what we've got here is we've got a situation where if I stretch my system by a factor lambda and I also dilate time by a factor lambda squared, the problem is eta would be invariant. So this will be a valid description of a problem if the problem is invariant under the same scaling. So imagine this initial setup with these boundary conditions. The concentration is uniform for x positive and 0 for x negative, and it switches at x is 0. When I stretch the thing, when I stretch the system in space, you can't tell, nothing changes. And if I also were to, and because this is at t equals 0, as I dilate time, the t equals 0 instant doesn't change. And so all that would happen if I stretched this system, well, actually nothing at all changes. The solution would be the same. Not all boundary conditions will be like that. But if the boundary conditions are invariant under this scaling, that means that the diffusion equation depends on eta only, the boundary conditions depend on eta only, and therefore the whole solution must only depend on eta. Okay? So it's called, if you like, it's a scaling method. Now let's have a look at this. So I've got this differential equation here. How would you solve this? We've already solved something a bit like this. What sort of ordinary differential equation is this? Tell me about it. Sorry? Homogeneous? No, because it's multiplied by 8 on the right hand side, not divided by 8 on the right hand side. What else? Tell me anything at all about this differential equation.
Can you take d by d?
Sorry? Ordinary, yeah, great. It's definitely ordinary. Good.
Linear?
Linear, definitely linear. Good. Second order. Is it second order? Is it second order? The highest derivative is 2, so it is, isn't it? It is a second order. But if I do psi, I'm just testing your Greek alphabet here. If I write psi as dc by d eta, then it becomes minus 2 eta psi is d psi by d eta. That's what you meant. It's first order. Actually, it is a second order differential equation because the highest derivative is 2. Sorry?
Do you have any like linear n order thing you can turn into a load of first order equations?
You can always turn it into a load of coupled
Yeah.
first order equations, not a single first order equation. Okay, this wouldn't work if there was any term in here that was proportional just to c, then this would work.
Yeah.
But because there's no term in c, because the lowest order thing appearing is the first derivative, then you can do this. Okay. This isn't going to cause you much trouble, is it? You just separate the variables. Is that right? So psi is psi naught e to the minus eta squared there. Okay? But psi is actually dc by d eta. So dc by d eta is psi naught e to the minus eta squared. Therefore, c is, let's call that k, just to avoid any confusion, plus eta naught, the integral from 0 to eta, okay, of that dummy variable. So I'm just integrating it up now, which I can write as k plus, actually no, it's not quite, k plus c1, I'm going to call it, error function of eta. Yeah? Which you recognise? Yeah? If I wanted the concentration to be, let me just, okay, if I said at t equals 0, when t equals 0, this becomes error function of infinity, doesn't it? So this tends to 1 as t tends to 0. If x is positive, I didn't draw you what error function is, but error function is an odd function because it's the integral of an even function. Yeah. So as the argument tends to plus infinity, this tends to plus 1, and as it tends to minus infinity, it tends to minus 1. So if I want, so as t tends to 0, this tends to plus 1 if I'm in the positive half. So for my previous thing, that's where I wanted C0 to be equal to the concentration to be C0 everywhere. To the left, on the left half, where I wanted the concentration initially 0, this would be K minus C1. Okay? And it's pretty obvious from that K is C0 over 2 and C1 is C0 over 2, and I've established my previous result. Okay? Of course, it could be more general than that. I could put two different concentrations. I could put a concentration for the left and a concentration for the right in here initially, and then I'd be able to solve for different values of this. But do you see that actually there were two ways to solve this problem then? I could use the fundamental solution and combine it and integrate it up and get the error function, or I could use this scaling approach. Recognise that in this particular instance the boundary conditions are of such a form that they're invariant under a particular scaling where x over square root 4 dt is invariant, and therefore actually just solve it. You know, under those scaling conditions, the solution has to be of this form. Just has to be. Okay. So that could be that in a way looks like a mathematical trick, But it does also have some physical significance, because actually the reality is that the solutions to the diffusion equation do take this form. They do depend upon this dimensionless ratio, x divided by square root 4 dt. And what that means is that if you've got similar systems, suppose I've got a system with characteristic length L and diffusivity D, and characteristic time for stuff to happen. Well, actually that would be set then by L and D, but let's say it's got length L and time tau. And then if I had another system which was alpha times L, then the solution in that system would be the same as the solution in my similar system, but at a time alpha squared times tau. There's a similarity, if you like, of the solutions if you scale space and time appropriately for the diffusion equation, and actually where things would look the same. So, you know, in experiment as well, you can do this. Right. Sorry, I'm just going to go backwards a minute. Okay. So we have a solution. Go back here. I said here. Let's just revisit these, and let's put C0. Let's replace by CR, and 0. Let's replace by CL. So CL is the left concentration at time t equals 0. CR is the right concentration at time t equals 0. And therefore it's clear that K is a half CL plus CR, which let's call that C bar, the average concentration initially, and C1 is just CR minus CL times a half. Okay. Which I could call a half delta C. Okay. And then in that situation, the solution looks like C bar plus a half delta C of that. There we go. Okay. I want to consider the situation now where I'm going to take an initial profile that is like this. It's a step up from 0 to C0, but instead of happening at x is 0, the boundary is at minus delta x over 2. Okay? And so actually all I want to do then is all I need to do is to shift my solution to the left by delta x over 2. So hopefully it's clear that this would have a solution a half C0 plus a half C0 error function of x plus delta x over 2 over square root 4 dt. Okay? And then over here, let's consider, again, something that is a little bit naughty. I'm going to consider a step down. Now, of course, concentration shouldn't be negative. but mathematically we'll get away with that. Okay, so it's going to go a step down at the point delta x over 2. So now I need to translate my solution to the right by delta x over 2 and turn it upside down. So it's going to be that. Okay. If I add those two concentration profiles together, I get this. Yeah? Where I have got a width delta x, and actually I've got a height 2c0 probably. Yeah? And it's centered on x is 0. So this is now a problem where the initial concentration profile is the sum of two opposite steps, such I've created a top hat. And I'm going to exploit the linearity of the diffusion equation simply to sum up the solutions again. And so if I sum them up, then the first two terms cancel, which is kind of what you expect, okay? Because they were representing the mean concentration, and now that I've only got a finite amount of stuff in an infinite domain, if the mean concentration is now 0 over the whole domain, and I've got a half c0 into the error function at x plus delta x over 2 for dt minus the error function like that. Okay. Let's now take the limit as delta x tends to 0, but where c0 times delta x is a constant. Okay. So I'm now going to take these two separate interfaces, squash them together, make the width of this top hat goes to 0, but at the same time allow the height of the step to increase so that the total amount of stuff, the total amount of material here is staying constant. So I would do that by saying that's a half c0 times. Well, I would just do an expansion. Okay, of here for small delta x. So that means it's error function of x over 4 dt plus delta x over 2 times the derivative of the error function with respect to x. The derivative of the error function was 2 over root pi, and then an integral of the Gaussian. So when you differentiate an integral with respect to the upper limit, you just get the integrand at that limit, and then a chain rule for the derivative of the argument with respect to x. And of course there are higher order terms, minus, and then the expansion of the other term, which is, there's two minus signs cancelling now. Okay, and so those terms cancel. You know what's coming, don't you? I've got a half c0 out the front. I've got two equal terms here, each of which is which amounts to, in the end, all of the 2's cancel, right? C0 delta x like that. Okay. In other words, I recover the fundamental solution. Okay. So that's another way that you could have got to it. Okay. So all of these methods for solving it are interconnected. Okay. Let's take a break there. Sine. Great. Okay. Now I want to try and apply what we've studied to actually solving a real problem. And the problem is a problem of precipitate growth. So we're back to our binary alloy. We're probably not going to escape that in this course. So it's AB. And I want to consider we've got a B-rich, so we'd call that beta phase, precipitate growing behind a planar interface. So this would be like a plate sort of type precipitate. Imagine a slab which has got this planar interface that is going to grow. And it's growing into a mixture, a phase which is rich in A. So it's alpha. So you can imagine this might be what would happen if you were in the miscibility gap and actually you have, you've got nucleation, if you like, of this B-rich phase. And of course, as the B atoms are getting accommodated into this beta precipitate, so their concentration in the matrix around them is going down, and so that's A-rich alpha phase. So, if I can draw this right. So, what have I got? I'm going to draw, this will be the concentration of, well, the concentration, we're just going to consider the concentration of one of the species. So I'm going to talk about the concentration of B atoms, okay? And it has a concentration C sub P, C precipitate, inside the precipitate. And this planar precipitate has some size S away from the origin, away from its center, okay? And the concentration profile, if it's growing, will look like this. Okay, the concentration of B at the interface is actually going to be lower than in the surrounding matrix because B is being accommodated into the precipitate. So you're sucking B atoms from just outside the precipitate into the precipitate. Therefore, the concentration of B atoms just outside the precipitate must be lower than it is in the matrix Cm. Okay, so here's the beta phase, here's the alpha phase. Okay, and we want this to be we're going to study a situation, and under this situation it's growing. S dot is greater than 0 because you can see that the slope dc by dx is positive just outside the precipitate. If dc by dx is positive, then the flux J, which is minus dc by dx, is negative, which means that the flux is going from right to left. So the B atoms, okay, the B atoms are diffusing down the concentration gradient towards the precipitate, and then they get sucked in and locked up, never again to escape. Okay. And that's what will happen if Ci is less than Cm, then that will be the scenario. You'll have a growing precipitate. Okay. If you had a shrinking precipitate, that would mean that B atoms were hopping out of the precipitate and they would be locally increasing the concentration above the average, and then this thing would look more like that, and the flux would then be away. So the B atoms would then be transported away, and that would be a shrinking one. Turns out we can't solve the shrinking one, but we can solve the growing one. Okay. The reason we can't solve the shrinking one is the boundary condition. See, this growing one, we can assume we start from nothing, and it starts to grow. That means that initially our solution will scale, it will obey those scaling rules. Whereas if you try and shrink an existing precipitate, then your initial boundary condition has a length scale, has a characteristic length scale of the size of the precipitate at t equals 0. and that means it doesn't scale. You start dilating that, you change the size of the precipitate at time t equals 0, and that doesn't admit the solution. Okay, so we need to conserve B atoms here. Okay, I'm going to want to be solving the diffusion equation here outside the precipitate, but there's no diffusion in the precipitate. Do you see? We're just assuming that the concentration is constant in there. Okay, it's just locked up in a particular composition for that phase. So what we must have is that here's the flux of B atoms arriving at the precipitate. Okay? Taken in a positive sense, even though the flux is negative. This is the number of atoms arriving per unit area, per unit time at the interface. And that, if they are going to be, okay, if they're going to conserve the number of B atoms, then that needs to be associated with this. Okay, the velocity with which the interface is advancing multiplied by the difference in concentration just inside the precipitate is how many B atoms per unit time are being sort of mopped up, if you like, and taken into the precipitate. Okay, and all of those atoms must be being supplied by the flux from infinity, because that's where they have to come from. Okay, we also, that's one of our conditions. We also have that the concentration at the boundary at time t is locked at being C interface. That's a constant. So wherever the interface is, the concentration's always got to be that value, and at time t equals 0, okay, we've just got matrix everywhere. We have no precipitate at all. Okay? And we're only going to solve it for the half plane, the positive half plane x. We're going to assume there's symmetry here. There's symmetry in the initial condition. So we don't need to worry about that. Let's revisit our step solution. Remember we were considering here and here, concentration to the left, a concentration to the right. And we had that thing that no matter what the time was, the concentration in the middle was always C bar, the average of the two. So if we're looking for a solution that satisfies the boundary condition, let me just write out what this solution is. This was C of x of t. It was the average times the difference. Okay. Then you see this boundary condition here, it wants us to have a fixed concentration for all time. Well, here's a solution that gives us a fixed concentration at this point for all time. Okay. This would be the precipitate. In other words, we're wanting to say, can we find a solution like this? So what am I saying here? What I'm saying here is, let's suppose what we want here is we want a solution for a half space, a semi-infinite half space, that decays to some constant value, like this decays out here to CL, and has a fixed value at the starting point. Okay? So that would look like wanting the average concentration to be CI, and wanting the concentration okay, we'll take CR. You can take CR or CL. Let's choose CR to be CM, just solve and you'll be able to find out what CL is. Okay, so this would have a concentration profile that looks like CI plus CM minus CI times the error function like that. Okay. There are lots of different ways of writing this. It's more convenient because CI is only the concentration at the interface, whereas CM is the concentration in the limit as something as x goes to infinity, and is the concentration where is close to the concentration nearly everywhere apart from the interface. You can flip this around. I'm going to write this in a slightly different way. Okay, I've got a new function here, the complementary error function. The complementary error function is 1 minus the error function. Okay, so if you put that in, you'll be able to see. And the point is now I've just got CM there now. That would be a solution. Okay, that's a solution that satisfies the conditions that I want. It's at x is 0, the complementary error function is 1, and so the solution is CI. So this would be like having an interface at x is 0 there. And as x tends to infinity, the complementary error function goes to 0, so the solution goes to CM. Okay? Like that. All right. And CI minus CM is negative, which is why this is sort of below, like here. But that's not the solution we've got here. You see, the problem we've got here is that this is not a fixed point in x. The concentration is fixed here, but this boundary is now moves in time. S is a function of t. So this is not the solution. That would be the solution if you just kind of held this boundary fixed somehow. But that's not the situation we've got here. So we go back, we resort to our usual method for solving differential equations, which is, what's our usual strategy for solving a differential equation? Integrating factor. Okay, that's quite kind of purposeful and strategic. No, I was thinking something else. Something you did before you ever heard of integrating factors. Ansatz. Ansatz is the posh word. What does ansatz mean? Guess. Thank you. We guess. So let's guess. Okay? Take inspiration from this solution here. And let's guess something now. What we're going to guess is the following. So CM, that's the concentration everywhere in the matrix. So that makes sense. We want that. Plus some constant now times the error function of x over 4 pi dt, like that.
Error function or complementary?
Sorry, complementary error function. Okay, and this is one thing we want to be valid now, not for x greater than 0, but for outside the interface in the matrix. Okay, now this does two things for us. If we look back at our original conditions, it does two things for us. It solves the diffusion equation, we know that, and secondly, it satisfies the condition that at t equals 0, it's CM everywhere. Okay, so it does get those two things right for us, but there's a couple of things it needs to do as well. At the interface itself, so at x equals s of t, we have c of s and t must be the interfacial concentration, which is Cm plus complementary error function times k of s over 4 pi dt. And that's got to hold for all time. How are you going to make that equation work for all time? Or if it does hold for all time, what must be true?
S must grow as
Okay. So we must have, if this is true, we must have S proportional to the square root of 4 dt. Now, that's the characteristic diffusion length at time t. So it's not unreasonable to assume that if precipitate growth is limited by diffusion, then the size scale of the precipitate is going to grow with the diffusion length. So it's not unreasonable, we might have guessed that. Let's write S is lambda times 4 dt, where lambda is one of those things we put in our ansatz, our adjustable guess, to try and make it fit. Okay, if we choose S is lambda times 4 pi dt, then C at S and T, which is Ci, is Cm plus K, complementary error function of lambda, and therefore that tells us that K, the other adjustable parameter so far in our ansatz, must be given by this. Okay? That's all right. So we've now satisfied the diffusion equation and two of the boundary conditions. The one thing we've got left is that S dot, the growth, was supposed to be limited by the flux. Now, from our ansatz, from what we've assumed the function of S is, we can now take a time derivative, and so S dot is lambda over 2 times root 4d over t, like that. Okay, which implies, if we put that into our conservation of equation, if you remember, this was Cp times Ci times S dot, which is that had to be equal to d times the derivative of the concentration with respect to time. So taking a derivative of this concentration with respect to time, this concentration with respect to time, okay, it's the diffusivity times K, which we found is Ci minus Cm over the complementary error function of lambda, times now the derivative of the complementary error function. Well, that will get a 1 over 4 dt from the chain rule. The derivative of the complementary error function is just minus the derivative of the error function. Okay? And it's the derivative, remember, it's dc by dx at x equals s. That's what matters. I have a feeling this might be one of the things that I've written up on Blackboard. I think because this is algebraically heavy, I did put a handout for this section of the course up. Okay? Is everyone happy with what I've done there? Do you see what we've done is we've been inspired by our step function solution to guess a solution for the concentration like this that satisfies the diffusion equation and one of the boundary conditions. We've then seen that to obey another boundary condition, we need to make the precipitate scale with the diffusion length. And then when we plug that in, so that enabled us to find K in terms of lambda, but we still haven't specified lambda. We now plug that into here, this conservation equation, and this has given us this very long equation, which if I fiddle around with it for a bit, and what I want to do is I'm going to gather all of the lambda dependent terms on the left hand side and all of the model specification parameters on the right hand side, all the concentrations. So I'm going to take square root of pi onto the right hand side, leave the lambda on the left hand side, take the complementary error function of lambda onto the left hand side. This here, this is lambda squared in the exponent here. So I'm going to take that over, is Cm minus Ci over Cp minus Ci. Okay. And if I draw a graph, so this is a wonky graph, so I'll continue to draw it wonky. Okay, this is what that function looks like. Okay, as a function of lambda, this left-hand side, okay, looks like this. It's not obvious that it would look like that. You've got an exponentially increasing function here, but it's times a complementary error function, which is actually exponentially decreasing, and you've got a lambda in there as well, so you can plot it out with Mathematica or something. What you can see is that there will be a solution to this as long as this quantity here, okay, lies between 0 and 1. Okay, if the right hand side lies between 0 and 1, then there is a value of lambda which solves that equation, and that then tells you how the thing behaves. Okay, and that will be true if CP is greater than CM. Is that obvious? If CP is bigger than CM, then the denominator is bigger than the numerator. It'll be between 0 and 1. And that was what we started out with by assuming that the precipitate was rich in B atoms. Okay, meant that the concentration was higher than the surrounding matrix. Okay, so actually this is now a new situation, right? This is a more interesting thing where actually you can now see, here's now something that tells us about kinetics and diffusion limited kinetics. We can see here now how the propagation of an interface in time is controlled by diffusion, and actually how we can solve the diffusion equation with this moving boundary condition actually to find the solution. So we can find a value for lambda, we can put it in there, therefore we know what k is, and we know that our solution at the top works. It can be made to fit. Okay? And really, the point that comes out of it is this one, that of course the precipitate boundary, the scale of the precipitate is proportional to the diffusion length. All I really did here was find the constant of proportionality. That is actually not that is not physically so important as just showing that the solution works. Okay, this actually holds. Okay, and in a way we could have probably argued that just from scaling arguments. Okay, because our initial condition was a vanishingly small precipitate, we knew our solution was going to satisfy our scaling requirements such that the solution only depends on eta. And if it only depends on eta, then everything in the problem has to have a length scale going like square root of time. Okay. You up for this? Spherical precipitates. I'm not sure I'm up for it, but let's have a quick go. For the spherical precipitate, for the spherical precipitate, we want to solve the diffusion equation in spherical polar coordinates. I'm going to have to do this quite fast, I think, here. Okay, and we're going to have a radius rather than big S. Now we're going to have big R. Okay, pictures would look the same. We want to have C at big R and little t. So that's the concentration at the interface must always be Ci. We want the concentration at time 0 to be the concentration of the matrix everywhere at that point, and we need to conserve material, so that looks like this. The concentration difference times the velocity of the interface, but actually now remember we had to turn a flux into amount of stuff, we have to multiply by the area, and because we're now in spherical polars, we can't just take a unit area of planar interface, we now actually have to multiply by the surface area of the precipitate. However, that doesn't matter because it happens on both sides. Okay, like that. All right. So, how are we going to solve that? How are we going to solve the diffusion equation? Because the diffusion equation has changed mathematical form now. But however, the scaling argument kind of still applies, doesn't it? So if I do that, yeah, you expect it to work. Obviously, you now have to plug this. You haven't just got d2c by dx squared on the left-hand side now. You've got all of these r squared things coming in as well. So when you do the transformation, which I think is in the notes, so I'm not going to do it now, let me tell you that what you end up with is you end up with d2c by d eta squared plus 2 1 over eta plus eta dc by d eta is naught. It's almost the same as before, but you have this pesky 1 over eta in here, and this has arisen because of all of these r squares and 1 over r squareds there. I think the stuff is available to deal with that online, but again, it is still only effectively a first order differential equation you're having to solve here. So plug that in, d eta by d d psi by d eta plus 2 1 over eta plus eta psi is naught. So that still is separable. Okay, so log of psi is going to be minus 2 log eta minus eta squared plus constant. So it turns out that psi is psi naught over eta squared e to the minus eta squared. Okay, and that's dc by d eta. And when I integrate that up, see, I can integrate that up by parts. Okay, if I integrate this by parts, where the dv is 1 over eta squared, then that will integrate to minus 1 over eta. When I've chosen u to be e to the minus eta squared. When I differentiate, I'll get minus 2 eta down, and actually the 2 eta that comes down from the exponential cancels the 1 over eta that is left from integrating up to get v, and they cancel, and also I just get left with e to the minus eta squared, which then integrates to the error function. So again, I think this is all in the handout online, so I'm going to skip through here. I get the following. Okay, so my scaling, in other words, all that's different here is the algebra. There's nothing conceptually different. Okay, the algebra is just different, so I don't want to dwell on this for too long. But again, this is essentially the same solution that we got for the step. Yeah, so it has the same properties. There's a point where the solution where it kind of has a fixed value, and it tends to a constant as r tends to infinity. So we guess, and maybe someone deserves a little bit more credit for this one really, we'll take our matrix concentration again, substituting back. Okay, look back at here, you see that in this solution you've got one bit which is like a Gaussian with a 1 over eta, and one bit which has the error function. Okay, we've done the same thing we did before with the error function in the planar case, where we've just switched it around for a complementary error function, so we can have Cm here. Here's the other term, which is the Gaussian term, divided by eta. Okay, so this is a form, again, this is a form of solution that obeys the diffusion equation, has spherical symmetry, and obeys the requirement that as at t is 0, you have this matrix composition. Okay, or as r tends to infinity, you do. The next thing was to say we want C of big R and T to be the interface concentration. Okay, in other words, if I put little r equal to big R in here, then I want it to be a constant in time, and everywhere in here, of course, you always get the combination r over root 4 dt. Okay, well, the 4's gone, but it's still r over dt there, root dt, r over root dt all squared there. So in other words, that enables you to draw the same conclusion, that you want big R to be lambda times the square root of 4 dt. Okay? So again, we find that the size, the radius of the spherical precipitate scales with the diffusion length. Okay? And that requires Ci is Cm plus k primed root pi on 2 error function complementary of lambda minus 1 over 2 lambda e to the minus lambda squared, or if you really want, k primed Cm minus Ci times 2 a bit more complicated this time, but still of the same sort of form. Okay? So in other words, this constant here will depend upon lambda and the difference between those two concentrations there. Last but not least, for the fun bit, Cp minus Ci times r dot, big R dot, the rate of the velocity of the interface, so again taking a derivative with respect to time of this, so I get a lambda root d over t from that, has to be d times the gradient of the concentration, that's dc by d little r, and when I take dc by d little r here, when I take dc by d little r here, only this term survives, that's a constant. So here is k primed, okay, and then you have to differentiate all of this. So I've got a derivative of the complementary error function, which gives me that, and then I've got to take a derivative of a product. So I'll start with the derivative of 1 over r. Notice that if you're following my algebra really carefully, you'll notice I've cunningly taken that 2 from the k prime into these square brackets and put it in there, just in case you think I've made yet another mistake. And then the derivative of the exponential. And the point here is that these terms, these two Gaussian terms, vanish. Okay, you can check that. And so you just get left. So actually this right hand side simplifies quite considerably, and it will come as no surprise that what we end up with is an equation like that. Okay? In other words, I get something very similar, it's just slightly different because of the spherical geometry. Again, I can look at lambda, I can look at 0. Again, there is a thing here. How's this going to behave at small lambda? As lambda tends to 0, complementary error function goes to 1, e to the lambda squared goes to 1, but lambda goes to 0. So this term vanishes as lambda tends to 0, so it's just 1 in the square brackets. So it goes like lambda squared. Okay? So it looks, that's not a brilliant drawing again. But compared with this one, which went linear at small lambda, this one is quadratic at small lambda. Okay? Again, there'll be a solution as long as this ratio of coefficients is between 0 and 1, which it will be under the same conditions as before. The fact that this goes like lambda squared rather than linear in lambda sort of pushes the function slightly to the right, sort of a bit slower to get onto its asymptotic trajectory up to 1. So that means if I've got a given ratio of constants here, what I mean by that is that one might have looked a bit, that's planar and that's spherical. Okay, so for a given value of the right hand side, the spherical geometry will have a larger value of lambda than the planar geometry. In other words, and the lambda is what scales the precipitate size. So it means, in a way, the velocity of the spherical one is faster. The interface moves faster there than for the planar one. Can you think why that is? Think why that might be? Why would a spherical precipitate with the same diffusivity, okay, for the same value of big D, so B atoms can diffuse in the same rate?
Because when you shrink it down, you have big volume that kind of,
Right.
you know what I mean?
I think I know what you mean, right? If you imagine the planar interface, in order to grow, B atoms have got to go from far away to the interface. And basically, if you pick any point, pick a unit area on the surface, on the interface, that has to be fed by an equivalent unit area of material at infinity, doesn't it? Whereas if you think about the spherical one, and now you take a unit area on that spherical surface, well, that can be fed actually by a bigger area that has the same solid angle, right? Yeah? So actually, if you like, because the spherical one is essentially a sort of finite precipitate in an infinite medium, there's more that it can take, it's as though there's more of the matrix that it can take B atoms from to grow, and so actually it's able to do that faster. Okay. So it's a slightly different thing. All right. Anyone got any questions? No? Okay.